Today's talk is essentially on water and food security related issues, which is kind of a very important issue for developing countries within the context of climate change, population growth, and so on and so forth. Interestingly, just a couple of days ago, there has been some short video clip which has been in circulation on uh, on social media, which is very relevant to Pakistan and portrays a very grim picture how things are. I thought of sharing that one with you so that you get a feel on the severity of the issue that we have to grapple with. So you got a bit of gist what we are facing, the challenge we are facing. And I do appreciate most of you have turned up today, which indeed makes the talk very relevant. And I hope that will be some impact coming from that talk as well. And then it does show the relevance of the institution as well. Now, without a further ado, I invite my colleague, Rita Memon, to please take the stage and introduce our guest speaker.
Hello, everyone. It's a pleasure to introduce Professor Ragab Ragab today. Professor Ragab Ragab is a fellow principal hydrologist and water resources management specialist at the UK Centre of Ecology and Hydrology. He was Vice President of the International Commission on Irrigation and Drainage from 2010 to 2013. He was the chairman of the UK International Committee on Irrigation and Drainage from 2007 to 2011. He was a chairman of the Permanent Committee on Strategies and Organisation, ICID, from 2011 to 2014. He was chairman of the Work Group on Water and Crops, ICID, founder of the Work Group and on the Use of Poor Quality Water for Food Production, ICID, 1997 until now. He is editor of Journal of Agricultural Science at Cambridge University Press from 2013 until now. Professor Ragab Ragab is recipient of several international awards and reviewer of more than 15 international journals. He is a member of the editorial boards for 4 scientific journals. Professor Ragab Ragab has developed 2 widely used models, SaltMed and IHMS. Without further ado, I'd like to invite Professor Ragab Ragab to take the stage. Just a note on the certificates, I will be putting a link in the chat, so if you would like a certificate, please fill out the link and you will receive one in the coming days. Thank you.
Thank you, Rita. Now, Professor Ragab, over to you, please. Share the...
Good morning, and good morning, everyone. Do you hear me?
Yeah.
Okay. Assalamu alaikum and good morning for everyone. My talk today will be about the water and food security, the challenges that we are facing and possible solutions. The food security as defined by the UN actually means that exists and when all people at all times have physical and economic access to sufficient, safe, and nutritious food to meet their dietary needs and preferences for an active and healthy life. That's really the I'm just trying to hide the photos that I have, so I have full screen. Just bear with me.
We can see your full screen. It's okay.
Yeah, but for me, still some photos taking part of my screen. So I'm trying to, yeah. So now it's better. So the next slide is that we are actually having now 1 in 7, they go to bed really hungry. And that actually triggered one of the Millennium Goals, that to end hunger, to achieve food security and improve nutrition and promote sustainable agriculture. And this is the 17 goals agreed by UN. And you will see that the Millennium Goal number 2 is basically to eradicate hunger or to end hunger. So that's really very important in connection with food security. The food security has 3 A's. One actually is the availability. The second A is accessibility. And the third is affordability. The current challenges that we are having now is that we have very limited water resources, and water demand expected to increase by 50% by 2050. We have also limited productive lands. 30% of irrigated lands are degraded now and will increase further. Also, we have limited nutrients such as phosphorus and potassium because they are mined. They cannot be produced chemically in factories. We have competition between biofuel and food for water. Also, we have food waste that amounts about 40%. We have also trouble to accept the biotechnology like GM for development of weatherproof pest resistance and use of non-conventional crops. Some farmers still resist that. Introduction to affordable, intensive, and precision agriculture. Also, we have the water, food, and energy nexus concept, and that should be implemented with the aim to produce water, reduce the water footprint, to produce more from less resources, as we say, more crop per drop per kilowatt per unit area of land. And also the other challenge that we have to double our food production to feed 9 billion by 2050. The climate change also predicted increase in vulnerability of agricultural sector in developing countries. Satisfying these demands while maintaining ecosystem, livelihoods, fisheries, and biodiversity is a challenge. The energy production carries a heavy water bill associated with pumping water for irrigation or treatment and desalination of water. The energy production in some parts of the world accounts for up to 40% of all water withdrawals. The increase in global energy demand by 30 to 40% and the global food demand by 70 to 100% by 2050 is a huge challenge. By 2030, 40% overall gap between the global water supply and the demand is expected. Now, the water resources issues actually presenting us with a list: too much or too little. Too much can cause flood, too little can cause drought and migration of community, as we have seen in the video presented a few minutes ago. Poor distribution can cause famine, as we have seen that in Somalia and Ethiopia in the past decades. Poor quality water can, of course, cause health hazards, and we have seen that in Bangladesh. Poor management can also cause competition between sectors and conflicts at national and international level. Now, if we look at the distribution of water and the share per person from 1950 to 2050, that you can see in 1950, the share per capita was 2,050 cubic meter per person. Now, this is reducing to 1/3 by 2050 to 4,500. So that shows that our really share of water is diminishing in terms of amount per person, and we have to be careful with that resource. Now, there is also another issue that causing pressure on water resources, that the population increase, of course, comes with increase in demand for food, and also the diet changing. There is greater demand now than before for thirsty crops, meat and dairy products, especially in Asia and in particular in China. Increased demand for out-of-season crops, melons and strawberries, etc. Nowadays, you can see those strawberries all over the year, winter or summer, out of seasons, and that's mainly really and also changing climate with more frequent drought events that also affects agricultural production and food production in general. Increased demand for biofuel crops, especially I've seen that in Brazil, that also takes the water that should have gone to produce more food. In the UK, as example of climate change impact, we have seen a different drought periods that goes back, according to the record, from 1798 all the way to 2018-19. So UK is known to be a water-rich country, not anymore. This country has been suffering over so many periods of drought, and that affects also the food production and would actually lead to increase of import of food to the UK. And one of actually the most memorable event that some people they refer to as really was all over Europe, not only in the UK, is the 1976 drought, where people in London and everywhere, they have been getting water from standing pipes in the street in just buckets for normally daily use. And as you see in the picture, that rivers were running dry, and it was really quite remarkable year. And the pensioners now, the people over 60, they remember those days, but the current generation, they experienced that in 2003, 2006, and 2012, and 2018-19. So still we are facing more frequent drought than before. This is example where the reservoirs were running dry in 2006, and the media started to pay more attention in the UK about the drought and how it affects the water reservoirs and the water supply for agriculture and domestic use. That's not only in the UK, but also we have seen that in California, where people actually, they protest for not having water and asking the governments to build more reservoirs to harvest water when you have a plenty of rainfall or when you have high flows. So this has happened in 2009, and actually it continues year after year until now in Arizona and also in California. In the UK, we had a project to study 7 catchments from Scotland all the way to Cornwall. And those 7 catchments, we have been looking at the record from 1962 all the way, 1961, all the way to now, and to see when the drought took place in the past, and how can we identify the gap between future water supply and future water demand. And we have been running a model that I developed some time ago. It's called Integrated Hydrological Catchment Scale Model. And in that model, we identified, when we applied it for the first time in Cyprus, we could identify the gap between the future demand and the future water supply. And that's actually led to the Cypriot Water Resources Authority to stop surface irrigation after they have seen that figure, because they were members as stakeholders in that project. And when they have seen that gap, they said, well, we cannot really afford to use surface irrigation. basin or a furrow. It has to be either a sprinkler or drip irrigation. We tried also that with another catchment in Italy, also identify the difference between supply and the demand over the next 50 years, according to the results obtained by one of the PhD students, that the groundwater is likely to decrease by 30%, for example, and the surface water, river water, by 28%, and fresh water demand would increase by 15%. So that would actually create a gap, and that gap has to be really narrowed or closed by other measures that we suggested. We did the same thing for UK as well, and this is really now in the process of writing publication. Now, the global agricultural production comes from rain-fed or irrigated agriculture. The rain-fed agriculture, actually, it is 75% of the total area, but produce 60% of the global production, while the irrigated agriculture, 25% of the area, but produces 40% of the global production. That shows how important to irrigate. I have seen now farmers in desert, like in Tunisia, Morocco, and in Western Egypt, where they started to irrigate olive and palm dates trees. Normally, these trees are desert trees. They don't need to be irrigated, but they discovered they can get more yield and more income when they irrigate. And you can see that from that graph, when you can have more income from irrigated agriculture versus only the rain-fed agriculture. Now, the approaches and possible solutions for these challenges, one of them is to improve water use efficiency. That would lead to a better use to the amount. You can produce more from the same amount. You can also increase the area that you can irrigate with the same amount of water. And now you have the efficiency goes all the way from the dams, where you have a lot of evaporation over dams, can be controlled. You have also, that goes maybe sometimes efficiency of 70%. And when it goes to the canals, some water also get lost in the canals through the cracks, through the sides. At the same time, when it goes to farm, and you have also some deep percolation to the drains, and also to the plant, you lose also some water by irrigating everywhere, not only the plant on its own. So you have, as you go all the way from the dam to the canals, to the farm, to the plant, there are some losses we can actually try to minimize, and by this we improve the efficiency of water use at different scales. This is an example here from Reading area near Wallingford, where I live, where some farmers, they have shared reservoirs and they cover them with solar panel, and this solar panel can actually produce electricity for their farming use, and also they release some excess to the public network and they get some money out of that. But at the same time, they reduce the evaporation, and that's the most important thing, that the reduction of the evaporation by floating solar panel is something really would help to improve the water use efficiency at reservoirs level. And also for improving the conveyance level, that lining the canals can also minimize the water seepage through the cracks in the walls and also at the bottom. Or also another option is use pipelines, and most of the Italians, they use pipelines. They don't really use open canals, and also I have seen that in so many countries, and I encourage them not to use open canals for water transport, but to use pipelines. So is a lot of people, they say why we need to improve water use efficiency, because what's lost upstream can be gained downstream. And there is a position paper in ICID by my colleague Chris Perry about this. This cannot really be of general application to everywhere. There are some places I have seen in semi-arid and arid countries where what's lost upstream never seen downstream. It's because the soil is too dry, and before you generate subsurface flow to downstream, you need to saturate the subsurface layers first. And these layers are too dry to actually to start to produce a saturated flow and to go all the way to the downstream. So yes, it is what's lost upstream is not necessarily gained downstream, and even if it's gained downstream, it will not be immediately available, not with the same quality and not with the same amount at the same time. You lose some water in the way. Also, I have noticed from my work in India in the Coventry Basin with the British Geological Survey that there is this connectivity between one place and another on the same basin or the catchment. So you pump water from one place, 50 meters away, you don't see change in the groundwater at 50 meters apart. So that means there is no connectivity between actually the groundwater locations in the same catchment, in the same basin. So the connectivity of subsurface layer due to sudden change of geology and stratifications may disrupt the continuous subsurface flow to downstream. And that's why we cannot guarantee that what's lost upstream can be gained downstream, and you shouldn't worry about water use efficiency. No, we should, and have been advising my colleague in so many countries, is to take water use efficiency a serious matter to save water to produce more food. Improving water use efficiency through accurate estimation of crop water requirement is important because a lot of people, they add water based on equations, not based on measurements. And when they use equations like Penman and Penman-Monteith, they calculate the potential evapotranspiration, and they add the crop water requirements based on the potential evapotranspiration. And if you look at the potential evapotranspiration, actually satisfies the atmospheric demand, but not the crop and water demand. And for that reason, in one of the EU projects funded, I have been using three instruments. One is the irrigation, which is the one to the left, and then the scintillometry in the middle, and we have the Cosmos ray, three measurements, three instruments for measuring really the actual evapotranspiration or actual soil moisture to determine how much really the crop water requirements is and when to apply. So the scintillometry is actually is transmitter and receiver that goes to send that infrared or microwaves from 1 point up to 10 kilometers, and you receive it at the end of that transect, and it would measure the actual evapotranspiration by the change in the air density along the transect, and that can be converted with some other parameters like radiation and so on to obtain the actual evapotranspiration. And that's actually the amount that you need to add, not the amount you calculate from equations that gives you a potential values. And when we started to look at if that actually makes a huge difference with the commonly used Penman-Monteith and the commonly used equations, I could see actually the actual evapotranspiration in some cases less than half of what we calculate, most of us worldwide, as a crop water requirements. So people who are using the equations that basing the crop water requirements on these equations, they are adding actually a lot more than the actual. And as editor myself of the Agricultural Science of Cambridge University, I received paper from young scientists comparing different water levels and the yield. And they come with conclusions saying, I added 50% of the ETC, and I got the same yield of 100% amount of water equivalent to ATC. And as editor, I do believe them. I do believe because they are basing the crop water requirements on a potential or atmospheric demand, not the actual crop and soil demand. And of course, 50% of something too much is also too much, because we always have been using equations and shying away from measurements. There are so many ways you can measure the actual evapotranspiration, not necessarily by scintillometer and edicovariance and other equipments like this, but there are cheaper methods that you could actually use to determine the actual evapotranspiration, and there is no problem to compare that with the equations and to make a correction factor. If you tend to use the equations for the rest of your career, that's fine, but calibrate it against actual measurements once, and then see what the ratio that you could apply. So there is no need always to go for the Rolls Royce if you have a Mini or a Fiat that will do the same job. This is another thing that we could use also for determine how much water to apply, soil moisture measurements. And we started by using cores, and then we went to neutron probe. And after that, we thought we're not allowed to use isotopes or radioactive source in measuring soil moisture. So we went to the profile probe, but all these measures are for point measurements. It doesn't really allow you to accommodate the heterogeneity of the soil. So we went to transects, and transects of 32 meters, 64 meters maximum, operated by the battery of your Land Rover. And we go and we measure the soil moisture content on a transect. But still, it is transect. It did help us with the remote sensing measurements. But with irrigation, we went to try something else, and that was the Cosmos. And the Cosmos system, it actually takes the natural rays of Cosmos, and from that, would react with the particles in the biosphere, creating neutrons, and those neutrons, they will be slowed down when they hit the hydrogen of the H2O of the water molecules. And that the more of neutrons slowed down, that gives us an idea how much actually water content in the soil. The beauty of that, it is non-destructive, represents a larger area, 300 to 700 meter radius. It gives you an integrated value of the soil moisture, and you calculate from that the soil moisture deficit, which is the actual amount you should add as irrigation. And we have about 52 stations now across the UK and Northern Ireland. We have some in China, and also we have some in India. Here you can see that you can convert the soil moisture of the top part of the figure, and you can see also the reaction to the soil moisture, the rainfall of the middle figure. And then the bottom one, it shows you the soil moisture deficit. When it's red, you should irrigate. When it's green, you don't need to irrigate, based on what the Cosmos can tell you. So if the Cosmos tells you, yeah, there is high soil moisture content enough, and that soil moisture deficit is low, there is no need to irrigate. But when you go to the amber, and then it means that you have a mild stress, but when really you go to the red, you can irrigate. So if this is put in operational system, that would allow you to use the water more wisely and improve the water use efficiency. Some publications about these methods and irrigation and drainage. They are here in front of you, and also that has been receiving a press release from Wiley to publicize the importance of these instruments and its importance for saving water. Another new Cosmos now appeared, a mobile system where you can pull it behind your Land Rover, and it can give you transects and also stop and measure, and the drive and the measure options. Now, more crop per drop, that's really what we are supposed to do to make a good use of each drop of water. And takes us to water productivity. We need to improve the water productivity. It means we have to produce more crop or yield from the unit water volume. But now that water and the crop, or more crop per drop, is now moved into a more integrated form. It's called the water food energy nexus. And the water food energy nexus approach is holistic vision for sustainability that would recognize and tries to strike balance between the different goals, interests, and needs of people and environment. And if you see the triangle, you have the link between water, food, and energy, because in order to produce food, you need the energy, because the energy is used to pump water, to irrigate. And the water is the center or the heart of that nexus. And increasing global food demand by 70 to 100% by 2050 requires an increase in global energy demand by 30 to 40%, while by 2030, a 40% overall gap between global water supply and demand is expected. So from this statement, you can see we cannot work in isolation. We cannot work only between water, focus on water and food, but we have to take on board also the energy into that, and that becomes now the nexus. We have to select the efficient irrigation system. If you look at the top one, the sprinkler irrigation, you irrigate the area between the plants, which is not necessarily to irrigate. When you go to the subsurface drip irrigation, you find that you are irrigating only the part near to the plant. So you don't really irrigate all the soil, only the parts where the plant is. That would save you a lot of water that gets lost by evaporation between the plants. Also, you can do that by alternating furrows and subsurface irrigation, as we'll see from the next slides. The other way, also rice cultivation. I conducted a workshop once in Malaysia about the water saving in rice cultivation, because paddy rice in Asia is really consuming a huge amount of water. And one paper actually won the award of ICID, is that one here that I'm presenting here. Two Egyptian scientists actually won that, where they can grow the rice on those type of furrows. So at the two sides of the furrows, they start planting the rice, allowing only 7 millimeter of water in the furrows. And you can see the rice, they got used less water, but also produced a good yield. There is also another thing to minimize the water losses by the irrigation, is by using a center pivot system with a very low level nozzles. So the nozzles can spray closer to the soil. And that's important, especially if you have saline water or treated wastewater. You don't want saline water to be sprayed over the plant, because the accumulation of salt after evaporation would burn the leaves. So you need to look for system that suits your water quality. At the same time, you minimize the irrigation, the evaporation losses. So this system, if you will lower the nozzles, if you are using center pivot, would allow you to make saving of 30% of the fresh water. A lot of people also use drip irrigation, surface drip irrigation, because it's easy to put the drip irrigation on the surface, just to put the line and then put the plants next to the dripper. But if you look now at the top figure, this wetted area will afterwards lose that water by evaporation, leaving crust or salts at the same area, that's wetted area. So in projects we conducted it's called the water for crops, we have been using subsurface drip irrigation instead to avoid these nozzles. And also it allows us to use saline water and also treated wastewater without really too much risk. And there is also example from the Americans in Texas, where they can grow cotton with using subsurface tape irrigation, drip irrigation, and minimizing the water losses by evaporation by the system. and also increasing the water use efficiency. We use something else in our projects, water for crops, by looking at if we can irrigate only half of the vertical root zone at each time. So we start by having twin lines, irrigating half of the root zone one time. The next irrigation we swap and we irrigate the drier half and we leave the one before. So we only irrigate each time one half and alternate that. We tried that in 3 crops, maize and tomato and potato, and it has been successful. And we could actually see there is a difference, 26% of the partial root drying method, water saving compared to the conventional drip irrigation, where you irrigate the 2 halves of the root zone. And also we found that we can save 40% or 44% when we compare that with the sprinkler irrigation. So you can save 40% water if you use the partial root drying method, where you irrigate half of the root zone in alternating way. Someone would say, well, drip irrigation is costly, but these are examples from Africa, where people they are using a low-tech and low-cost drip irrigation, and you can also get the same really results from those low-tech and low-cost. Another thing, of course, to control the amount of water by using a credit card like the one used for the bank, and those credit cards can, by the water authority, determine for each farmer how much water he or she can get from the hydrant at the top of the field. So this is decided by the water authority for, depending on the crop, depending on the area, they will give you a credit card, and you are only allowed to use that amount of water allocated for you. Increasing water supply is another solution for the challenge we have. How can we increase the water supply? One of them, of course, is rainfall harvesting. That's the obvious solution. And we tried that by collecting rooftops rainfall on houses near Wallingford, near where I did. And there are 3 publications in urban hydrology about that, how you can do that. And then also harvesting water at micro catchments and also macro catchments, where we actually, in the micro catchment, we could make it to be terraced, and at each terrace we put some crops to grow there. In large catchments, we tended to have to use our valley, which is the lowest part of the catchment, to grow most of the crops. Fog harvest is another option used somewhere in Latin America. In Brazil, I have seen the underground dams where you make trenches and then they put thick plastic sheets between the 2 trenches, and then that would actually allow any rainfall to stay between. This is what you see after they put the soil back. So it means between 2 trenches there, that any rainfall will remain between these 2. There will be no horizontal movement of water between one part and the other. So what would fall as a rainfall will remain between those trenches. This, they call it the underground dams. In some parts in Africa and Asia, also they use zays or pits, and they make those holes just before the rainfall comes in, and then when the rain comes in, then we'll have these holes where you can put actually your trees or your crops in between, in the middle of those zays or pits. And this is an example from Cambodia, where the school children actually they do that exercise by making the holes and planting what they like to plant, and leave them until the rain comes in and gets into those holes to irrigate the plants naturally. We also used those circular bunds in Tunisia, and also they are used in Burkina Faso, where you also harvest the rainfall and to use it as a continuous supply to the plant or the trees. We have been also involved in a hydromet project, where we have been looking for harvesting water in mountains at that sort of scale that you see on the picture. And actually it has been successful, where the farmers, they came closer to the lake to have their own agricultural areas and to start to produce food. Another sort of water supply is to use non-conventional water resources. And that could be drainage water, brackish groundwater, wastewater that's treated or untreated sometimes. I have seen that in Morocco. Industrial treated wastewater, mining water, I've seen that in South Africa. Breweries, Kingfisher beer in India, we managed to convince them to use that water for irrigation. Food packaging industry, sugar industry, fish farming, wastewater, all that can be used and reused for irrigation. And when it comes to saline water, if you look at the fresh water that's available in the world, it is only 1%, and the rest really is saline. And the most of that water actually is under the ground. So saline water is a huge amount, and we hardly make use of it. We try to use the saline water by irrigating tomato, and here example in salt milk project, where we allowed the farmers in Egypt and Syria to use saline water, and also in Malaga, Spain, we used also in the same project in cherry tomatoes, and we discovered actually these tomatoes, they have higher sugar content when they are irrigated with saline water. In Aqua Biosaline Agricultural Center, they have been producing barley and pearl millet with saline water up to 15 decimens per meter. Another way of also using drainage water, agricultural drainage water, is to recycle that. So you irrigate the water with the least tolerant plants first, and then collect that water from the drain and irrigate another crop that has more tolerance level than the previous one, collect that water afterwards in the drainage and irrigate it with a more tolerant than the previous one. And then after that, when the water becomes too saline, then you can actually use that to irrigate halophytes. And the halophytes can be atriplex, can be Bermuda grass for feed and other things. And if really the salinity is too high, then you can get rid of the salt through evaporation ponds. Another thing we did, this is example from the Water for Crops project, and in India we have been using from sugar industry the wastewater and using it for irrigation. And also we did the same thing with the brewery in Hyderabad and Bangalore to irrigate crops. This is another thing we used it also in Egypt, where a colleague came to work with me in the UK, and he managed, Dr. Abdul Rauf Ramadan, and also he managed to use the drainage water of aquaculture and fish ponds to irrigate the crops. And actually he found that the yield was much higher when it's irrigated by drainage water of aquaculture, because it contains a lot of nutrients, and that helped to have a more yield. That has been published in 2017 and won the Best Paper Award by ICRD and Wiley and some publishers. Another thing we did in the project of Saphir is also to collect from smaller community the wastewater, and then to treat that wastewater in a container, and that container would purify that water to the level suitable for irrigation, not for drinking water, but suitable for irrigation, and it has been used for growing some crops and also growing vineyards, as you see in the picture here. And that container was done by stakeholders, Danish companies called Grundfos. And here, this is a container in Crete, where the small community wastewater can come in from one end of the container, gets treated by filtration and chemical, and then UV at the end, and then would produce water suitable for irrigation to the smaller community. And this is really how that Safir project was producing. And the sort of water that's really good enough, not for drinking, but for irrigation purpose, it would meet the requirements. Treated wastewater can also be used for people who are not keen to use it for food or for crops or salads. They could use it for olive trees, orange, and peaches. And this is an example from Tunisia. And now, if you can, was our colleague in ICARDA, who was also a member of the project, they compared the income of what we get from using treated wastewater for wheat, faba bean, and vegetables, and you can see the benefit really of using treated wastewater, because it is rich in nitrogen and potassium and phosphorus, so full of nutrients, and that would give you a huge benefit compared with fresh water. The use of non-conventional crops, we have been encouraging people to use less water-consuming crops, to also encouraging them to use drought-tolerant crops, salinity-tolerant crops, use rotation of deep and shallow-rooted crops, and heat and colder-tolerant crops, wind-tolerant crops. We have been encouraging people to use that sort of crops. And this is an example of two crops. They are very nutritious, like quinoa and amaranth. And we have been using these crops in Turkey and North Africa, and even in the UK, as drought-tolerant crops. They use a lot of less water, and they are also saline-tolerant. And this is here a graduate in the UK from Harper Adams University who established his own farm for quinoa, and is now distributor to UK and beyond the UK, the quinoa as cereal crop to the rest of the world. Precision agriculture can also help to have a more efficient of water use and distribution. And this is also from another project where they use telemetry system, sensors. They can measure the soil moisture, and then they send a signal to a server, and that server could actually send a signal to the irrigation control unit to start irrigating when the soil moisture drop below a threshold level. Another thing is leveling your soil, so you have a good even distribution of soil moisture when you irrigate. So nowadays you have those tractors equipped with sensors, and you can have a nice leveling land to make sure that each part in the field gets the same amount of irrigation or rainfall. Nowadays they use drones as well, and you use drones to see the need for fertilizers. For example, if part of the yield is getting yellow, it means there is deficiency in nitrogen. So you know that part has deficiency in nitrogen, that part. Also, you could use the same drones to detect the need for irrigation as well, and then you irrigate when you see there is some symptoms that indicates that the plant is really in need for irrigation. And also water quality now is monitored in Australia by those drones to see if there is really some change in the color of the water, indicating algae blooms or anything to act immediately. Another thing that we also use is the salt melt model. I developed that model in 2002 for EU project, but it continued over 4 projects, and that actually can handle all irrigation systems and can handle also all water quality and all salt types. And this is free download model. You can download it from ICID website, or if you go to Google and you write salt med, you will find more information about that. It can give you all the calculations of the processes: evaporation, water uptake, leaching, nitrogen, crop yield, crop rotation, water use efficiency, water productivity. Can also gives you the development of the water and salt under the soil surface, and also gives you the total dry matter and total yield. You can download that from the website of ICID, and also there are special issues that, as you see in that slide, you can have a lot of information about the model. And the model, of course, can give you, if you run the model as what if scenario, it will help you to use the water more efficiently. Can also help you to choose the monitoring system that you need. The frequency of measurements can also help you to select the proper crop that suits the resources that you have. The field management's mixed cropping is another thing happening here now in the UK, where you have a strips of one crop followed by another, and that would encourage actually the pollination. And increasing pollination, it means increasing yield, at the same time reducing also diseases. So this is something now happening in the UK, would actually produce more food. In terms of food security, it's really more important to have that mixing farming system. Also, this tillage now getting more important. Suitable tillage practices like conventional tillage, mulching, leveling, plowing of crop residuals, manure application, amendments, precision input like low input would also help. Monitoring system of nutrients and soil moisture is important. The agro-environmental wildlife strips at the edge of the field to enhance pollination rate. We have here an organic farm in Wantage area in the UK, where they have 6 meters strip around the field, where they encourage, they don't grow a normal crop in that strip, but just wild plants, and they are flowery plants most of the time to encourage pollination. They get subsidy for that, and if the farmers would allow 12-meter strip, will get double of the subsidy from the Ministry of Agriculture and Fishery, because they improve the wildlife, especially for insects, and they would increase the butterflies, bumblebees, and so on, and those are, and wasps, and those, they are quite helpful in pollination and improving the yield. And one advantage of this conservation tillage is that you reduce the soil evaporation by increasing water availability below the soil surface. You increase the organic matter, you reduce the soil erosion, you increase the nutrient availability, you reduce the agrochemicals used through the recycling of the crop residues, and also reduce labor and machinery, and improve wildlife. So that's really one of the benefits of having these conservation tillage, or sometimes they call it minimum tillage, sometimes they call it zero tillage. So what I said now, there are different possible solutions for really improving the water use efficiency and increasing the food to meet the food security. So there are so many switches really we can switch on, but you have really to be expert enough to switch the right one. And as a closing remark, that I have seen that in The Economist saying that feeding the world, if words were food, no one would go hungry. So what we need really, not words, what we need is actions, and the actions are needed and now. Thank you.
Thank you, Ragib. Quite an inspiring talk, and especially the conclusion. We got to move beyond words.
Yeah.
Ragib, I have got a quick question for you. Can you hear me?
Yeah, I hear you. Yeah.
Okay, great. Now, these kind of fancy solutions, of course, they are practical as well. And then you did mention some examples from India to Egypt, and some examples from Africa as well.
Yeah.
My question, or I just want to understand the uptake beyond the research projects. of these solutions in those developing countries? Have there been any monitoring, or how is the situation?
Well, some countries really have been adopting the some of the solutions, uh, and for example, the Iranian in Ahwaz area, they have been adopting the PRD, the partial root drying in sugar cane cultivation, because they are suffering from both salinity and water shortage. In Mauritius, for example,
Go ahead, Nopo, please. My question, I am from Pakistan. My question is that what are the challenges around water?
can I hear the question again? What is?
Sir, my question is that what are the challenges around water? Around the water?
What the challenges?
Yes, yes, sir.
There are so many really challenges around water. In Pakistan in particular, you have really water shortage in so many areas, and you have more brackish water in so many areas. And I tried with Professor Fayaz to write a proposal is really to desalinate the brackish water and to use it in Pakistan in particular. So there is a problem really in different countries, but each country has its own problems when it comes to water issues. Some countries have water, but a river, like Egypt, 99% of its water comes from the Nile, while some other countries, they don't have rivers at all. And the problems would be is the reliance on groundwater. That's the case of, for example, Libya. They don't have rivers there. Tunisia, they don't have really big rivers. So their reliance is more on the groundwater, and they don't have much rain. So here you have a problem with how much recharge goes in there, how much renewable rate to the groundwater, how can you make the balance between the recharge and the abstraction for countries where, or regions where the only source is the groundwater. So the problems really differ and they vary from one country to another.
Thank you.
Sir, second
We
question,
have new question. I think we have to give turn to other people as well. Now the next question is from Hassan Haider. Hassan, fire on.
Hi, sir. My name is Hassan. I'm a graduate civil engineer from Karachi, Pakistan. Sir, I would like you to comment on the importance of aquifers in the water crisis. What role does the aquifers play in to curb the water crisis? Actually,
What the rule?
what is the role of aquifers? Aquifers are the source of underground water table.
The aquifers.
Yes, sir.
Yeah.
The aquifers that we have really is, I don't know, of course, it differs from one country to another, but there are aquifers at depths that really economically very unviable really to produce water from. I have seen aquifers that more than 1 kilometer below the soil surface, and that's really economic and technical challenge to get that water. The other thing is that what's the quality of that groundwater as well in order to invest to get the water. If the water is not renewable, like the case of South of Libya and Egypt, the groundwater there of sand is an sandy, Danubian sandy stone aquifer that covers Egypt, Libya, Sudan, and Chad. It's only fed from north of a Chad lake, and the Chad lake itself is shrinking because there is no much rainfall. So these four countries, they have shared aquifer, and that aquifer, the water really is brackish at a deeper depth, and at the same time, the quality is not really great for really intensive agriculture. because if it's not renewable, what you take to irrigate will never go back to the aquifer. So we have really to be careful there, because that needs sustainable management. But at the same time, you have to think about future generation. If you are using this water now, then you left nothing to your grandchildren to use. So you have to be careful with really using aquifers that's not renewable, and to try to think about more innovative solution like desalination water at reasonable cost, and also to use crops that they don't use much water, use irrigation system.
Okay, great. I think now, thank you, Ragib. We are running really out of time. There is considerable interest, and I can see lots of raised hands here. Maybe 3 more questions, very brief questions and brief answers that will help. So the next question, I would invite Umar Farooq Bullo. Please fire on.
Thank you very much, Professor, for your highly valuable lecture on the water and food security challenges and possible solutions. Grateful for your insight and teachings. I'm really helpful very much understanding what you have said about the current situation and the future challenges considering the water scarcity, and especially in those areas which are now getting more water and food scarce owing to increasing demand, and likewise. So my question is that using of the technology, specifically in those countries and regions who are poor, to have to bear the cost of the things that may reduce the water usage, specifically the drip trickle irrigation and the sprinkler irrigation, at the same time the lining of the channels, and the so many methods which we can reduce the water usage by applying the new method technological advancements, specifically understanding the crop soil relationships and the moisture contents and the permanent wilting points of the specifically when the crops are drying. So in such scenario, would you kindly suggest the cost efficient water application methodologies in the poor countries, specifically the country like we people, where we have also the uneven the water irrigation water distribution modes are more political or administrative?
Okay, so Umar, Professor Ragib, is there a silver bullet? That's the question, I think.
Well, the silver bullet really for most of the countries is to accurately estimate how much water I need to apply and when to apply. And that's really the big question for any person in the world using irrigation system. And I think the new method, the new techniques that I presented, in the long run, they actually they can recover the cost. And most of these systems are mobile, so you don't really need to stick them to one field. At the same time, they measure larger areas, so they are cost effective in the long run. But at the same time, you can also find a suitable solution by, for example, some people use lysimeters, and lysimeters also a way to calculate how much you need to apply and when accurately, more than the equation.
Yes, I think that's very well said. Now, Umar, we will be circulating Professor Ragib's slides a bit later, which will have a bit more details on his contact and other resources. If you have got interest and for the sake of implementation in developing countries, we are very welcome to engage in more dialogue on that one. So the next question is from Imran Ali Channa. Please, Imran, go ahead.
Yes, sir. Sir, are you listening to me?
Yeah, we can hear you. That's fine.
Sir, I have a question regarding to our country. This is, of course, less developed country or a developing country. I have a question from Sir Ragab that can we rely upon some empirical calculation in the absence of some advanced instrument, as sir showed during the mid of presentation, the scintillometer and the eddy covariance.
Yes, you could, of course, in absence of these new technology. I need that because my relative humidity is that level and I can go up to 100%. And that's completely different from when you ask the plant or the soil how much water you need. So you need to calibrate these equations. And to calibrate them, you could use a small experiment, like lysimeter experiments. And the other thing, you could apply different levels of what you get from the equation. So you apply 80%, 70% of the calculated evapotranspiration by the equation, 6%, 50% as experiment, and then you come to the point at what point really excess water does not bring you more yield. So that would be the solution if you don't have that Rolls-Royce equipment.
So maybe Imran Sheikh, you can go ahead. Kindly unmute yourself.
Thank you. Can you listen me?
Yeah, go ahead.
Okay, great.
I'm Imran Sheikh, and we are working on sustainable rice production in Pakistan. My question to Rajab is that do you think that sustainable is economically viable for a farmer, for a common farmer, which has nothing incentives from policy level or from private sector level? The initial cost of working for sustainable needs of working capital, that is because sustainable is not in the policy framework of the government like countries like Pakistan. So do you think that it is only in our country it is a project oriented only? If you have a project, then there is a sustainability, otherwise it is considered that a sustainable is a subject of environment, and a public sector, private sector does nothing. So do you think that what will be the future of sustainable? And second is the rice. In our context, we have a land where only rice can be grown. And if you go that, some people say, actually getting a lot of water in rice. What that farmers can do where nothing can grow other than rice, flood-prone areas, soil and humidity, and a lot of other things. What is your opinion? Thank you.
Well, first, let me start by the word sustainability. There is no sustainable source.
Yeah.
Let us agree on that. Sustainability refers to management. So, because a lot of people, they mix between sustainable resource, there is nothing is called sustainable resource. Everything is finite in our world. And as we say, madayim illallah. So for that reason, that we are talking about sustainable management. When it comes to hydrology here in the UK, we define the sustainability with a time span, and that time span cannot exceed 50 years because this is the maximum for us to forecast. So 30 years will be better. So sustainability should be associated with time span. So any government or any regional officer, when he or she does a sustainable management plan, it has to be associated with a time span, until what time, and how we are going to manage up to that point, and what we are going to achieve, what model actually we are going to use. So for that reason, sustainability is a plan, and a plan over a certain period of time, and you know what the milestones are and what you're going to achieve. So that's really my view on sustainability, but it is a management sustainability, and I would insist on the fact there is no sustainable resource, but what we have, or what we are talking about, is sustainable management, and it can be done, but it has to be linked to a time span with milestones and achievements.
Okay, great. Thank you, Ragib. I think on balance we should take, because we have got considerable audience on Facebook as well, and then there have been some questions there, but I will pick just one from there. The question is, how can we manage soils that are saturated with brackish water? That's
Yeah.
kind of a very open question, isn't it?
No, it's not really open question.
Okay.
I faced that at my younger uh, years when I started to work on north of the Nile Delta in American project where it was the same. And what we came about with is to have, we had a clay soil, by the way, heavy clay soil, and we had salinity issue and shallow water table. So the first solution is to have a drainage system, to put in place a drainage system. Without drainage system, you cannot really improve the quality. The other thing is that we had to plow gypsum, which is calcium sulfate, to plow it in using subsoiler. And the calcium would actually replace the sodium that absorbed in the clay, and the sodium will become free to be leached out, because the sodium is the ion that's responsible for low infiltrability of the water, and that's why you get that waterlogging. So we need to get rid of the sodium that causes waterlogging by replacing it with calcium, and we've been adding calcium sulfate plowed into the soil, and also establishing the drainage system. In some areas, we managed with the normal classical drainage system,
Yeah.
but in some areas we
Right.
have to
And
apply.
I think the question also came from expert Khalid. You might be knowing him. So the question came from him. The last one, this is the absolute last, very brief one from Saad Gul. Then we are done. Saad, go ahead.
Hello, am I audible?
Yep.
Yeah, my question from Raghav is that where he sir mentioned that in his presentation that we can use saline water for the crop production. My question is that if we use that saline water, will it affect the end product quality? Because we are getting the quantity by raising tomatoes, but will it affect the quality of the tomatoes by using that saline water?
Good one. Raghav?
Yeah, well, we use the saline water that was a level that close to the tolerance level of the crops that we used. So we have been applying also using a variety of tomato. It's called the Trinidad, and that's known to be a saline tolerant. So you need to know the tolerance level of salinity of the crop, and you know the salinity level of your soil, of your water, and sometimes we diluted the saline water to make it to match the maximum tolerance level of the crop that we are using it for. And for that reason, I'm going to give a talk with Dr. Khalid Mahmoud webinar on 29th of September. So if you are really interested in salinity, maybe you should listen to my talk and on a Tuesday, organized and coordinated by Dr. Khalid Mahmoud. And I'll be talking more about the salinity. Actually, the talk is about management of saline water.
Okay, thank you, Ragib. I think now we conclude here. But before we do that, two things. One is we thank our honorable speaker in our usual way. I wish we were not virtual, were physical, you would have heard lots of clapping, assuming it's happening. So thank you very much, Ragib, for all your efforts and so much time despite being on Sunday. Did very well. And your talk has been very well received. And I have been told that in today's meeting there were some decision makers as well from Pakistan regarding irrigation systems. So this may spark some interest, and then we will be bridging and bringing people together, inshallah. The last thing, the information about the next event that we have is on now I've shared my screen. You can see the next event is on 11th of October. The talk will be given by Dr. Paveen Ali from Sheffield University. and it is going to be more on female in science and technology, and then the issues and opportunities for developing countries. I'm very mindful that we have got considerable number of female participants even today. The main thing is that that talk is not going to take place 2 o'clock as is the normal case, but from now onwards, the Pakistan time will be at 4 p.m. So I think this is the main another announcement which I have made. Thank you for your time, which is very much appreciated. And now we close the meeting. Have the best rest of the day. Thank you.
Thank you for your